Let's start. Welcome, welcome, welcome to the second time series Estonia meetup. I will walk you what you are to expect today. We're going to start with two talks. Have a short break, then have another two talks, and afterwards you will be allowed to play with a wicked robot outside. Please go to our partner's Mash machine, play with the music, very amazing. And of course we're going to have some drinks and networking afterwards. About our speakers, we have a great lineup. So we have Ricardo, who is a research fellow at the University of Tallinn. He's going to be talking about the history of stream processing. We also have James from TransferWise, who will be talking about observability at TransferWise, and his speech is called "The Problem of Not Being Observable." After the break, we're going to have wonderful Anastasia talking about observability at Spotify. She came especially for this event from Sweden. We're so happy to have her here. And last but not least is going to be my co-founder presenting an interesting case about data-agnostic monitoring, data-agnostic observability, based on growing peppers. So, we want to thank our sponsors and partners without whom it would be impossible to make such an event. First of all, as you see, it's Playtech, Bolt, TransferWise, and Influx Data. We also have some wonderful support in terms of food from Hummus House and Taste of Brazil, Brazilian Mindset, as well as Mash Machine about music, and Veini Man's Tallinn. They're doing a great craft cider, so please try it. It's really cool. We're gonna do this the question session. You can all download the Slido app, and please enter a code G339, so you can submit your questions during the speech, whatever you're interested in, and we will pick up the most popular ones, and then after the speaker has finished his part, we will then ask a couple of questions. All the speakers will remain after the event, so feel free to grab any of them, also us as a team of TimeTricks, to ask any questions. And since it's the second event already, and we thought maybe we just tell you what actually TimeTricks is about. We haven't done that the first time, so TimeTricks is essentially a high-performance engine for modern telemetry. It's an open-source observability solution, and observability is something that we're going to be talking about today. But digging deeper and not staying with this, nice words, we see ourselves as an ultimate tool for critical information of the state of your business. And we get that through insights from the data that is generated from your normal IT operations. This allows you to react quickly and avoid costly downtimes. And yes, it's about anomaly detection. We are able to send you near real-time alerts, and near real-time I mean less than a second, so it's pretty quick. On any changes in your data, be it a product outage or be it a payments failure in your business. Some of you would say, guys, you're like a Datadog or a New Relic, but it's not quite like this. We actually don't alert on anomalies, we alert on anomaly patterns. It means that we don't need to set thresholds on metrics. What we do, we use flexible ruling to cover complex conditions in your data. We call it flexible rule systems, like really creative this, I know. But through this, we are able to work with data that is very cardinal, seasonality, principally out of the box, so it's pretty cool. We are data agnostic. It means that we work with all the systems that you usually use in your operations. It could be streaming, monitoring, analytics, be it Prometheus, be it ELK or Google Analytics, and we can send alerts to your existing channels, PagerDuty or Slack or whatever you use. We see ourselves as an analytical layer on top of your stack, and we give you the possibility to detect changes and correlations in your data patterns. We work with any data that has statistical regularities. It's a lot of technical words, but I know. Basically, any data that relates to behavioral patterns. Imagine you using Uber app, or business KPIs, as already mentioned, like payment failures or production outages, or IoT, manufacturing 4.0 or smart homes. We based our engine oriented on stream processing, and Ricardo is just going to talk about this in a second. And the true beauty of it is that it's highly, highly efficient. We are 1 or 2 orders of magnitude more efficient than our commercial competitors. And to give you just a slice of understanding what I mean by that is, if you are a small to medium enterprise, your usual cost or resource cost to maintain a proper observability solution would run up to something like 70K, let me say. With our engine, which is open source, your cost, and this cost is without licensing, of course, but your cost is actually only 1K. And with one small machine, the beauty with one small machine like that, you can tune up to 10,000 events a second. Sounds a lot, but Google search has basically 20,000 events a second. So it's a massive, massive performance waiting for you out there. This flexible rule system, what we call it, and the ability to dig down into the deepest and the highest granularity of data that you have allows us to produce a very high quality of signal to noise ratio. It basically allows you not to be overwhelmed by false positives. And talking about false positives, we want to talk about dashboards. I mean, everyone is overwhelmed with dashboards. But unfortunately, the problem with dashboards is that the more the merrier comparisons are not applicable in this case. We watch too many dashboards, we watch red sea of alerts, but we're not acting on them. And we say, dashboards are useless, yes, but just track what's really critical for your business. Just let everything else go, forget about it. And even though we don't see ourselves as, kind of like a tool to improve your DevOps practices, we actually want to place ourselves as being and covering your back on the most crucial intersection of your business and its interaction with your clients. I think everyone wants to have reliability and trust, and this is something that we can't provide you without engine. And we're not just a company, because we're just a bunch of guys from different companies who gather up, and we feel the pain of on-call production noise. Well, everyone knows the problem. It just sucks. And we're here to solve this problem. We're an open source solution, as I already mentioned, and we are not yet live. We are have fully functional backends, and we're just fighting with UX and UI issues, but we are truly, truly expecting to go fully live, place everything in GitHub somewhere around April. But if you think that what we do is pretty cool, and you want to contribute, you want to speed up the process of the product coming to market, and maybe our product can help you or your company show better performance and be more efficient, please give us a note. Please let us know what you think. Let's just chat. We will be on Startup Day in Tallinn next week, so if you are unable to get hold of us today, please send us a message, and we'll definitely arrange something to meet you in Tallinn next week. And having said that, we're almost done. I'll give you just good advice for best practices. And we have already arrived to our first guest speaker. As mentioned, he's a great guy. He's a research fellow at the University of Tartu. Welcome up and give it up for Ricardo.
everybody. I would just pretend not to be nervous. I already spoke about in front of a crowd that big, but they were all academics, so nobody was listening. So I hope this time I convince you more about what I'm doing is worth. So before we start, just catch up a bit. Who am I? So I'm Riccardo Tomasini from Italy. I just moved to Estonia in November. So it's a working country, I'd say. I work on stream processing and AI, but today I will just touch the first part. I'm a lecturer in Tartu, and I would like to talk with you about also any study-related things if you want to go back to university eventually. This is how my talk is structured. It's called A Brief History of Stream Processing. So the idea is picturing what happened in a huge state of the art that started in the beginning of the 2000s, actually a little earlier. And this is a timeline. I'm seeking for precision, not for recall. The idea is that we have seminal papers across 20 years of history. Actually, we stop in 2019 and count this one. We won't start with all of them. We want to just start with the most important one. And the first one, the story started in 2001 with in US at Stanford. There was a girl called Jennifer Whedon who had an idea. He says, why don't we stop storing data and we just query them as soon as they arrive? Kind of crazy at that time, but it was motivated by a good reason. Storage at the time costed a lot, right? Unfortunately, they didn't have much memory as we have today, so the prototype was kind of small, and the system was called Stream. It didn't take off immediately. It was a good paper, of course, good academic result, but not much in terms of industrial impact. We need to wait a bit more. We need to be in 2005, when Michael Stonebreaker, how many of you know his name? 2? 1 or 2 people? 3? Okay, more? 4? Okay, good. That's coming up. He's the guy behind VolDB, if you ever heard about that system. He's a cool professor who smells impactful research lines and decided to branch out startups that usually sells to major companies. Well, in 2005, he understands that stream processing is gonna be a big thing in the upcoming years. And he writes this paper, which is the vision. 8 requirements for real-time stream processing, which is about how the analysis is going to change over the years to meet these requirements. We don't have a system yet. We don't have a solution that we can actually use. But already the idea is pervasive in the industry, because this guy is the gluing element between the two different words. So we're back to our timeline, I promise. I'll be short on this. There are some other events which are important in the story of stream processing. Well, this one is the first, and we'll see it in detail. CQL is the first actual query language that appears, and is again from Jennifer Whedon. She decides that you cannot just process data on the fly by writing a piece of code. Not everybody can do that. You need to democratize. So what she does is that she designs a language which is an extension of SQL, because she has a strong background in databases. The language is called continuous query language and allows you to write these queries that last forever. They never end. Continue to push out results out of an input which is infinite, because it's a string. And finally, we have some takeoff. 2 years after the Stonebreaker paper, we have a change, a forced usable thing, because there is a prototype that you can pick. It's called Stream. Stanford Stream Processor. So we go back in time a bit more, further in time a bit more, and we have other important event. It's 2008, it's again 12 years ago, when stream processing crosses the path of AI. And this is about my research. There is an area called stream reasoning, which tries to combine logical, rule-based reasoning with real-time pre-stream processing. Unfortunately, the algorithms to reason on the data, to deduct things, are not very scalable. They take a lot of time to compute. And stream processing requires, or maybe better, it advises you to process data very, very fast, because your information needs have time constraints. So the research here is tricky. You want to have complex business intelligence running in real time. And we are 10 years, we are working on this problem. We have many solutions, we have systems ready to be used. We'll talk about this maybe offline, because I want to focus on the pure stream processing part. Few years later, stream processing crosses the path of AI again. And this, you might have heard about this more closely than the former one. How many of you know MOA? Nobody, one person. How many of you know Apache Samoa? How many of you know Spark ML? Okay, so Spark ML is based on Apache Samoa, which is based on this work by Albert Buffet in New Zealand, who actually now is Paris Tech, who understands how to compute, actually retrain constantly a model without losing latency in the results. It's based on one concept, actually, sorry for the pun, the concept of concept drift. How many of you know the concept? So basically, long the data change, your model starts giving errors, giving problems. Solving this issue, the concept drift, is critical for stream processing. You want to retrain as fast as possible when you realize that you're going to be wrong soon. So that line there poses a new landmark, a new important event. It starts appearing a new word that you might have confidence with. It's a word, actually 2 words, or 1 word, depends. Big data. It's 2013-12, when the word started being mainstream. Everybody starts talking about big data. We have data everywhere. How many of you have worked, say, I work on big data? How many of you can tell me what big data is in 3 words? 1. You can tell. Pardon?
Doesn't fit in R.
Doesn't fit in R. What else? Anyone else?
Volume, speed.
Oh, my guy. Volume, variety, and velocity. That's the thing. So, big data is about three challenges. Velocity, process data which are coming too fast. Volume, the first original one, processing too many data. And the third one is variety, processing data that are very different from each other. So you cannot rely anymore on data model optimizations. You cannot say, okay, the data are going to be tables, so I can optimize right indexes. You need to clean them before you process, and that's the big deal. Hopefully you don't have all the challenges altogether, practically you always have them. So at this point, new system came up, and a new model came up. You might have heard about Apache Flink. You might have heard about Apache Spark, is the first one. Other system, recent Kafka streams, Apache Samza, all Apache things. Actually, they like stream processing apparently. So, but there are many more. So what I show today is just the tip of the iceberg. There are Niagara, Aurora, and many other Telegraph CQ, many other systems that populate the state of the art. Now, our focus today will be on 3 of them. 3. I try to give you a perspective of the pillars of what we do today. This is important why for you that are not academics like me. Because if you're going to approach Flink, Kafka Streams, KSQL, any of these new tool or toys that you're going to play with, you will have some, issues in understanding the concept behind it, because they look like something that you know already. Companies work hard to cover them behind friendly interfaces that don't break your comfort zone. But the system works differently. And what I call the intended semantics, the expected semantics, might not be the one that the system actually has. So our focus will be on stream and tables. Actually, let's go on The CQL model, the continuous query language, the very first one. The data flow model from Google, which is the system behind Google Dataflow, and also Link. And stream tables, or also known as the stream duality, which is the model behind Apache Kafka, actually Kafka streams. What do you think? It's too ambitious to do 3 of them in 30 minutes left? I don't see you very well, so you have to be a bit loud. Yes, it's difficult, so I should go home. Okay, let's try. I hope it's not. What's up? Okay, no. Okay, actually it's not that hard, because these models are compliant to each other. The first one, the continuous query language, is about the application. It provides a language that you can use for do what today we call data science, to analyze data. It's like SQL. You give it into the hand of domain expert with a technical background. Okay? The data flow model, the one from Google, gives us a system perspective. It teaches us how the system behaves. Down there, it actually computes the different continuous procedures, how it manipulates the data, the foundational concept behind it. Stream table, this is my favorite, is a new hope, if you're a fan of Star Wars, or is a hybrid perspective. It stays in between and trying to glue the system work with the language work, with the application work. And it solves a lot of problems to me. If you want to understand the problematic behind stream processing, this is the way to go. I hope I'll guide you through this. So, the goals of the system are different. The first one, CQL, try to recycle a lot from the world databases. It tries to be simple, clear, yet strong language that you can use for doing everything you want, and efficiently combine 2 things that you might have known already. One is data streams, and one is relations. So it works only on relational data. And here you might already understood that it doesn't work with big data, because you cannot expect data to be relational anymore. You need to put them in that model. The data flow model on the right is that it's supposed to work for correctness. You want to understand how your system behaves, what it does, because all these systems introduce one concept that we'll see in a minute, which is time, that makes everything more complicated. Third, data flow model is also optimized for latency. You want to reduce as much as possible the time you have to wait for your response. The model in between is actually focused on latency as well, but take data distribution and ordering into account finally. You don't just focus on parallelism, but you want to consider those two. And you want to avoid the semantics of implicit operator. So everything is implicit. It means that you know exactly what you're writing, and the optimization comes afterwards. So let's start from the concept, which is the trickiest one. I'll guess cluster in the beginning. So when you will stop listening to me, I hope you didn't do already. You already got the main ingredient. All these systems have time. All these models have time, and try to introduce it into the different approaches for stream processing, but they do it a different way. Actually, they couldn't even agree on the terminology. These people, 10 years separates data flow model from CQL, and 5 years separates the data flow model for stream table. But, you know, man, 5 names for the same concept, for real. Right? One guy once said, 2 hard problem in computer science, right? Caching, validation, and naming things. So, in CQL, we have the concept of clock time, which is the time of the machine assigned, as the machine assigns the element it receives. It gives you a strict ordering relation of your elements, because it's a single machine that assigns that. It's important because when you want to process a stream, you need to reduce the amount of data you are taking into account, because it's infinite. And to process an infinite structure, you will need infinite memory. Second is the source time, which is the time of the data when they actually got produced at the source. If you imagine a sensor measurement, the time assigned by the sensor to the measurement, that's the source time. And finally, you have the source head bit, which is the time that arrives from the source that tells you, look, I won't tell you anything else that is, it comes before this moment. This is needed by who processes the data because he wants to be sure that he didn't forget anything for the process. Now imagine you are counting the observation of people who enter this room. You need to know when to stop. And if the observation you're receiving is stuck in the ether because your network has some lag, you might do a wrong calculation. Now, there are some events you don't want to miss, like this meetup, for instance. The second one, the data stream model, like that. Oops. Is where I didn't do it. Okay, go back. No. Magic. The flow model introduced two new concepts, the logical order and the physical order. They're actually the same as before. The logical order is the order of the message according to when it was done, when it was produced. The physical order is the order of the message when it arrives in the system. Again, the same concept that represents 10 years after. And we have the same in the data flow model, which is the one I will use now on because it's the most clear. The data flow model introduces three concepts. One is the event time, which is the time when the event was produced. One is the processing time, which is the time when I start processing the data, when I receive them. And the third one is the ingestion time, because you might want to ensure that all your messages are strictly ordered. So what you do, you're going to put a big bottleneck in front of your system that receives everything and order them. That is the concept of ingestion time. So far, so good. This is the most. Now you can get drunk. So you are alive. Nice. I had classes that were more loud than you guys. So please. There's one thing we should also talk about. Sorry, I move here because I need to. Let's see again now. It's the concept of watermark. How many of you heard about it? No, you lie. Everybody heard about it. Because I just told you that this is something called source timestamp. Okay? When the source tells you, look, you don't have to process it, you can go processing because I won't tell you anything else that happened before this. The watermark is the same idea. It's the relationship that occurs between the event time, the timestamp when it happened, and the processing time, when the system starts to process. Of course, you have a delay, because the system, an event is observed in nature, say, again, our measurement by sensor, and then go through the network and arrive to our stream processor, right? So that's a physical lag, we cannot do anything about it. But we could put the stream processor in the sensor, but then we have to get results. So it's the same thing. The idea is, you would like this relation to be as linear as possible. You have like a fixed delay, but that's not true. Okay, so the ideal one would be the diagonal of this graph. Okay, actually what happens is that you have spikes. Some moment you're very low, you get all the messages, sometimes your network is busy. So the watermark is a logical instrument that the stream processor uses for deciding itself when it's okay for start computing and discarding all the messages that arrive afterwards with certain timestamp. This won't be useful if your stream processor is in a single machine, but if you are dealing with a distributed system, out-of-order arrivals are by design, because different machines have different clocks. So you must rely on a logical order. You have this problem constantly, even if everything goes fine. Okay? So if you want to scale, if you want to process massive data, and that's the case with the 3 V's, right? Volume, velocity, and variety, you have to take this into account. Not much to do else. Alright, last common slide that we dig into. What is the domain language of these three approaches? CQL uses two concepts, stream and relations. Relations should, actually it's time varying relations, but for now let's consider relation as you studied them in the first year of computer science, like tables. The data stream duality model uses strings again, and it branches them in changelog and record. We'll see what they are. Keep in mind that a changelog is something that describes a change. And tables, so quite coherent with the CQL. And the last one uses something called P collections, when P stands for processing. Please go away. No. Please go on. Parallel, because it's a very low level. It's actually inherited by Flume Java. How many of you heard about Flume Java? 2. Okay. CQL, in 3 slides, we try. So I told you we have strings. A string is an unbounded sequence of data, never terminates. And this is a tuple, okay, like a piece of a table, and a timestamp. So far, so good. A relation is what's written there. So, I mean, yeah, I teach, so I have to remember this definition, but it's a set of tuples where each element is a domain. Domain is the space of the data. You can think about numbers, strings, whatever you want. Okay? But actually not true, because the relation, it's time-derived, it's a mapping from the concept of time to the concept of relation. So for every time point you have a function, you pass this time function, and what it returns is a relation. So I'm afraid I won't do that in 4 slides. I need a couple of slides more. Sorry. Because I see your faces are a little flexed. It's very fine. So we have strings and relations. Okay? So how do we go from string to relations? Well, it's easy. We just string to relation operator, right? Well, they don't have much fancy there, these guys. And what is a string or relation operator? A sliding window. Have you ever heard about it? 1, 2, 3, 4. Come on, it's popular nowadays. In the world of relations, once I compute this function, which is what someone called materialized view, I can simply apply relational algebra, right? Whatever I want, like join, selection, progression, whatever I find useful. But to go back, I need special things that are called the relation to stream operators. Can you guess what this operator do? Do we have time in the world of strings? Yes. How many yes? 2. I suppose that the other one I need. 3. Okay, we have representative also on this side. Do we have time in the world of tables? No, we have this function that abstracts that out. So the string, the relation to stream operator attaches the percent. That's it. So let's start. This is a sliding window. I think I need some slides, sorry. How it works. I have a nice stream of events, and this is my intended relation work. So what I do is that I define a width, okay? And this is my scope of computation. And I call it W. And then I have, I move over the strings. As soon as the time arrives, I move, and I take all the elements in the last 10 minutes. The question is, how often do I move the window? This is called the slide, and I call it beta, okay? Because I am calculating letters. And that's it, it moves. So, a string to relation operator is an operator that chunks the string into finite portions that I am able to compute with standard computational tricks. Because that's it. So no big deal. But it does that forever. Okay? How do I go back? I have 3 ways. I'm going to skip this one because time is not much time. Just to know that each of these operators attach a different timestamp to the output. Okay? The flow model. I hope this time I don't want to break your promise. I won't do that in 3 slides, which were actually 5, but 7. But I will do that in less than 42, and no worry, this is an overestimation, I promise. The data flow model uses 4 questions, so it's very easy. what, where, when, and how. I'll have to read them for you because you can read yourself, but I want to explain them. So the what tells us about the processing model. It tells what is the stream about, which is again, key value pairs. Before we have tables and timestamps, now we have a message and its key, okay? And is represented by a P collection. Very generic, I don't know what the element is agnostic from its model. The what is a concept of P-transformation, a parallel transformation from one P collection to another P collection. Everything is string to string. I don't have to go to the concept of relation anymore. I can transform directly. But let's create a problem, because what if I have stateful computation? Where do they go? Everything that transforms something infinite into something infinite doesn't have a concept of state with it. So big deal. How do I solve it? Are they cheated? Well, I can do three things in this case. I can do element-wise transformation. That's fine. They don't require infiniteness. I can do aggregation. I can sum element-wise to strings. Doesn't require any state. I can compose. Composition requires state. And then it comes the when and the where. The where is the windowing again. But this time, the where tells me conceptually where I have to locate my data using processing time as a measure. So I have three windows in the model of data flow. I have the fixed windows, called tumbling. I have sliding and sessions. Where these are the sliding ones? The session ones are cool because sometimes you want to compute things that are not regular in your string, like login sessions of user activity strings, things like this. This is a simple example of the window model that assigns to each element to a window. And then upon this, the window represents a P collection that you can actually transform statefully. So the where model is a bit tricky because you drop the timestamp here too. And after that, you can merge window, compose them, and do pretty magic stuff in this case. I'm gonna stop this part because it's a wall of text, and I promised myself years ago I won't tell about them anymore, but I keep them for reference. So if you want to study afterwards, that's it. I give you homework. There was one thing left actually too, the when and the how. The when and the how are about an orthogonal model called triggering model. It allows us to trigger the computation. In the world of CQL, that was not necessary because it was the windowing sliding that was triggering the computation for us. Here, we need to establish that externally. Because once the data arrive, we assign them to each window. But the window is just a box. It doesn't tell us what to do with the data inside. So we have a third element, the trigger, that computes the when and the where and the how. The when tells us using even time. So the element message, it's time to compute, dude, and is usually triggered by the watermark, the one we saw at the beginning. The how instead, it's a bit different. It explains us what kind of answer we can give up front. Because if we allow out of order arrivals, we might have to retrieve the answer we gave before. Because something changed in the past, and we need to recompute all the messages and say, no, look, I was wrong about that. So we have different options, discarding, accumulation, and accumulation with retraction. Each of them does different things. One case you ignore, or you can, correct your results constantly. So big deal. So I'm a little tired, although after all this math, I hope you're not tired too. And was that too ambitious? Yeah? Well, I'm not done. You there? Too bad. Time is left for this guy, which is my favorite, and I'm gonna screw out of it. No worries, I won't kill you. The data dual stream model aims at seek for simplicity. This is the design space. You have the cost and the completeness, and it tries to stay in this space here. Okay, you want to give you simple primitives, such as this. Here you go. I have to skip some slides. bytes. So you have two abstractions we named them before: the stream, the table, and the strings. Actually, change the string. So what you do is that you can move from one table to the changelog by capturing its updates. Okay, so seeing add one, remove one, add one, imaging people on a table, counting people in this room. And then you can materialize the result using a stream processor that takes them on and applying the sequence. The concept is in between, because you can have, here's an example. The moves of the chess keyboard are your updates, and the current status of the chess keyboards is your table. It's very simple. If I know the list of moves starting from a beginner position, I can reconstruct the current state. As simple as that. How do I do that though? As a simple animation that shows it. Sorry. So you have the table, Alice 1 appears 1, Bob appears 1, Alice appears again. These are the stream of things happening. The thing is, the beginner stream is about facts, observation you know. When you observe the table, it's a bit different. So, what we talk about is a change stream when you observe the changes. But when you are consuming the sensor's data, you are observing the records. Like I observe temperature at 25 degrees at timestamp day. So I need other operations to move from this kind of strings to the world of tables. It's a little trickier. Okay? There is an actual problem that the table are not a real table, but like a collection of tables, one copy for each moment in time. Just back to the world of time per eye relation we saw at the beginning. So you're like a time machine. We can navigate through the table and see the snapshot we were interested about. How do we move from one another? Here is the model. We have, from the record stream, we apply stateful operations, such as filters, map operation. How many of you do functional programming? Okay, is there. So map operation takes one element at a time and modify it. Or if you want to move from the world of streams to the world of table, we need to be stateful. And here we apply again Windows. We have the concept of join that requires the assignment of a window, a chunks stream, and move us to a finite portion of data. The complete picture. So I have a stream of observation, the records, I have the table representing it, and on top I have the changeable stream. See the different nature of the two elements. I need to reconstruct them. So, is there any way for me to go from the world of changelog to the world of streams? No, that's not possible, because they are intrinsically defined. A changelog stream is a stream where every element has a key, and the key is not unique. When you give me a message with the same key, I will override the one before. Instead, the record stream, every message has a unique key. This conceptual difference in the model forces us to have different operation over them, and we cannot do anything about it. You all end up in this situation, and that's it. We didn't solve it. So, mapping to Kafka, very quick, then I cut off. A stream is just a topic. How many of you know use Kafka? Good, so I don't have to recap it. A topic is a logical organization of your data, a queue. And we can align a record stream to a copy directly. We can align a table to a copy directly if we compact it. If we take only the last occurrence of messages in Kafka with that particular key. Similarly, we can observe the changes, consuming the same concept, a compacted topic, as a changelog stream. I did it nicely. It's a summarizing table, if you want. You tell me I have to finish. It's okay, it was the last slide. Okay. So what we saw today, just the tip of the iceberg. I hope I didn't bore you to that. It was fast, I know. But I hope we have a little bit more clue about what are the ingredients of today's stream processing. We saw three different things, and I think the last one we saw, which is hopefully the one that lasts more, is the one you need when you start approaching these kind of technologies. If you work with Kafka already, this work will probably help you understand it a little better, especially Kafka strings-wise and KSQL. If you don't know much about Kafka, we are starting a chapter here in Tallinn and in Tartu. Please subscribe to it, because they told me that until we reach 50 subscribers, I cannot start an event. So, yeah, we're in Confluent. I'm the log organizer. Of course, Alex and the other will help. Everybody who wants to help is super welcome. I'm not just like the action, we didn't do any leadership. So please join this one, take a picture, and I hope you ask me questions if I can kill you too much. If I didn't, thanks for listening to me, and I'm hiring PhD students and master students. So if you want to do a thesis with me, I will be very happy. Constant crossing, of course. Right, question? Good question, right?
Well, I was actually going to applaud. So.
Okay.
I have actually a question. What's the relevance of your scientific research for the computer science group?
Say yes.
What are you doing in
Sorry, what is this answer?
Is it working? Absolutely. What are you doing in science? Why is it relevant for the computer science field? What impact your research might have?
Right now.
Yes, in Tartu University.
So I'm sure. So what are we doing right now? What impact is asked on what we're doing right now?
On what are you doing as a researcher at Tartu University?
Okay. That's more needed. Yeah. So what I do is trying to mix this with AI. I specifically work on the logic part. So if you think about what Alex presented before, the rule part, like how executing fast rules that do deduction and reaction on things like this, it's a tricky problem. So I specifically work on these things, and I'm doing a bit of online machine learning, but I'm really just at the beginning. There is a problem there. So my specific work is more on the logical aspects related to, I don't know, how many of you know Datalog? Nobody. One person. You know everything, Alex. I know. You study at night. I know. So I work on the logical aspects. So like how to do complex reasoning on top of these things very, very fast. And right now I'm also working on graph databases. So what I would like to have right now, I'm working right now, is how to compute cipher queries in streamings. That's the current project. Like graph stream processing, something like that. Actually, theses are open on this, so we'll have good people.
Thank you.
Thanks.
All right, so I think we have another time for one more question. Anyone? Or otherwise we will proceed. Right. Oh, there's one.
Yes, like what stack are you currently using for programming languages or tools, like for your research? Or
Which language I use for research?
Or stack in general?
So nothing extremely obsolete, but unfortunately, and don't kill me, I have to work in Java at most, because most of the tools for logic are in Java. I don't use Java as well. And for the front-end aspect, we use for the data science on top of this, because we do a lot of data science on top of these things. We use Python, SQL. But the core system are built in JVM languages. Yeah. So.
All right. Give it up for Ricardo. What a great talk. Thank you. And we're moving to our next speaker, and it's a guest from TransferWise, and he's going to talk about the problems with observability at his company. So give it up for. Yeah.
So hi, I'm James. Just got the clicker right. Yeah, there we go. Cool. All right. So in this talk, I'm basically just going to talk about a little bit of the history and context as to why TransferWise needs a bit of observability, and also some tips that I have people who want to try and implement it in their organization. So a little bit about me. I am a site reliability engineer. I started at TransferWise in very early 2018, and then sometime in the very late 2018 we established the observability team at TransferWise. So what we do is maintain a monitoring stack, and we also do a little bit of social engineering. We try to do a lot of blog posts internally, we try to interview people, try and find out what their problems are, and we also try and build libraries to try and make the transition from traditional monitoring stack to observability a little bit more easier. And if you're happy with the vagueness of this talk and like what TransferWise is doing, we're always hiring, so check that out at some point. So it's always good to start a presentation or talk about observability by first defining what it actually is and how it applies. So there's two definitions which we tend to hear, or at least I've heard, which I sort of categorized into the vendor definition and the pure definition. So the vendor definition is the one that you'll hear from New Relic, Grafana, and so on and so forth, which basically boils down to there are 3 pillars you need to care about. This is only tracing, metrics, and logging, and once you have all of those, you are observable. This isn't necessarily true because it basically boils down all of the problems that you have in a distributed system, just the pure technical ones. It sort of describes all of the problems that you have in a distributed system through aggregations, or if you're very unlucky, you'll get all the data all the time with no possibility of actually sampling or getting what you actually want. And so as a result, actual investigation of problems that happen are, you basically have to be a domain expert of your service to actually do anything with it, and it makes onboarding new newbies and having them on call a bit of a pain in the ass, and so on and so forth. The definition which I like to use, especially at TransferWise, is the pure one, which is often quoted by charity majors, which takes the control theory approach that your system is not observable until you can determine the state of the service through its outputs. And when you dig deeper into what that actually means, it seems very close to what monitoring actually does. But it's not exactly the same. There's a few key differences, and the main one being is that monitoring tends to focus on known unknown problems. So these are things which you already know the question to and expect an answer for. So things like, how much RAM does my service have? What is the network latency? How many requests are done? These are all questions that you know about. These are all questions which you can get from standard monitoring tools. Whereas unknown problems, which is the one which observability focuses on, are more abstract and a bit weird. So things like 10% of users in Romania are suddenly finding that they can't use your service for some reason. Why is that? Who knows? Or you have a cluster of about 500 VMs in AWS, and 10% of them are going to experience some sort of disk outage. So why is that? Who knows? These are the kinds of problems that observability wants you to try and help you answer. And the way that it sort of encourages you to do that is to think of your distributed systems as socio-technical problems. So you can have all the monitoring stack, that's absolutely fine, but then you need to have the social aspect of this. You need to have constant feedback loops in order to make sure that when you have problems that you actually fix them. It needs to have complete ownership of the pipeline. You need to have all sorts of squishy things that most vendors do not give a shit about because they're vendors. And the way that you actually sort of investigate the kind of problems which you get in observability is through aggressive sampling. So at its purest, you are viewing actual data that comes through your system unmodified, but at an aggressive sample. So instead, it's basically the entire request of life of a request that travels through your distributed system, but not all of it, just some of it, which makes it incredibly more useful than aggregates, where you can't really determine where something has happened, or fire hosing, where you can't possibly see the forest for all the trees. So, why does TransferWise need observability? Like, what does it look like architecturally that requires this kind of approach? So, instead of giving you diagrams, I'm mistaken to tell a story. Oh no, I've lost my background. That's hard to read. Okay, anyway, so from 2011 to 2017, TransferWise basically looked like a standard LAMP app. It was one server, one monolith which served all the customers forever. And then as the business grew, we basically started extracting some of the stuff out of that monolith and turned it into smaller services and so on and so forth. Very simple stuff. Traditional monitoring was applied, so just like a normal health check monitoring and stuff like that, just so that you can get an overview of what the system's doing, whether or not it's actually working. It was good at the time because the amount of services that we had and the boundary context was small enough that anyone who came into the company could basically keep the entire thing in their head. And whenever there were problems, you could basically just ask anyone and everybody would probably know what the problem was. This is what I like to describe as village-sized problems. Basically, like, you know exactly what's going on, everybody sort of does. So from 2017 to 2019, we sort of, well, as every business sort of grows, you sort of realize that having a small set of services isn't really good anymore. So you start breaking up those tightly coupled business domains into smaller and smaller chunks. And so the communication between them starts getting more complex. The knowledge it takes to understand the system starts to become incredibly more complicated. So as you progress through this sort of fragmentation, it makes it very few people end up knowing the entire state of the system. Very few people can conceptually hold all that information in their head, and it almost always tends to be SREs who manage the platform. God bless their souls. The other thing is that the traditional monitoring approach doesn't really work at this point. You start falling into distributed system problems where, like, you need to monitor more than just the health checks. You need to monitor, like, the networking, all the other kind of beautiful stuff that happens. This is what I call a city-size problem, and you may be getting a hint for what's coming up next. Wow, city-size problems. So basically, same thing, the progress of our sort of breaking down services continued. Now we have 300 services here at TransferWise. It's very messy. I have no idea what anything is doing anymore. The relationships between services is so convoluted that I couldn't, like, even if we built you a map, it would look like a steel wall, basically. It's pointless to show you it. Once you've seen one, you've seen all of them. So that's the kind of thing that we're dealing with. And in the future, it's going to get worse. So we need things, we need observability to actually be able to sort of reason what's actually happening with our system. So TLDR for that entire spiel. I have no idea what our infrastructure looks like. It probably looks like this. Oh, actually, because the background is lost, there's actually some text there. It says, it probably looks like this, and it doesn't matter. So this is Monzo's networking architecture. Monzo is a challenger bank in the UK. They have 1,500 services. We probably look similar to that. So with that context in mind, here are some of the things we learned in transitioning away from village-sized problems to city-sized problems. The thing that I personally learned is that distributed systems are hard. Prior to coming to TransferWise, the most services I ever had to deal with was 10. Now I have to deal with 300, and I have no idea what I'm doing half the time. But you learn, after getting thrown in the deep end, you sort of learn to deal with it. And what I've learned is that distributed systems ask incredibly random questions at you. Like, why does our site break every Monday of the first of the month? It's a really random question. So this is what I was talking about the convoluted architectures. So this is TransferWise at about 100,000 feet. You have the website, which does all the things that you would do. You would log in and you would make a quote, and you would log into your account, transfer money, stuff like that. You also have the API, which allows you as a customer to be able to do all the things you do on the website, and it also allows business users to do roughly about the same thing. TransferWise is served by a cloud of services located somewhere on the internet, no idea where, and each of those services is also backed by a database, also in the cloud somewhere, no idea where. It's not important. So every first of the month, what we start to get is an increase in the amount of traffic that we have. So, as usual, we start getting alerts like, hey, we're starting to see more things in our system. And naturally, as what happens in distributed systems, one service falls over, and so the person on call for that service goes, oh man, I'm just gonna scale it up. Surely no problem with that. So scale up the system, and hopefully everything should be all right, except when it's not. What ends up happening is that because the networking relationship between all of these services is so complicated, the upstream services and the downstream services now have more capacity to fail. So as more and more people are coming into our site on the first Monday of every month, we start having a cascading failure across the website. And eventually it looks like this, and no one can use the website, it's really terrible. All of our engineers spend quite a lot of effort trying to get everything back up, but for strange reasons the API still works. Who knows why? Because distributed systems are weird like this. And every engineer basically looks like this for about 5 or 6 hours. So what exactly did we do to try and answer this kind of question? So we have data about the fact that we have some services falling over. We have data about how much traffic they received and so on and so forth. But it didn't really tell us why it was falling over. Yes, having so many more users is great and all, but it's worthless. You need to have a bit more context as to why things are going wrong. So we explored what data we had. We started to instrument some of the user flows that happen throughout the system. We identified the top services that people start using, and we instrumented them. We started tracing, we added more logging, we added more of everything. And as people start getting more data, we're able to make more data-driven decisions. So when the first of the month came around again, why does our site break every first Monday of the month? The answer is, the first Monday of every month is payday. That's why we get so many users. And the reason why the site fell over is because one bad query on one service, where it turns out that when you have an influx of users to that particular service, it starts spamming the database and it can't serve requests. So when you start adding more services to that pool of service, it basically kills everything, and then it has a cascading failure effect. It's very terrible, and it was basically fixed in about 3 hours. And we had this for about 3 or 4 months. It was terrible. So one of the things that we learned from this particular incident, happened several times, is that monitoring for unknown unknowns is technically foolish. A lot of the times when we were doing incident reviews for this particular incident, it was always like, we need to monitor everything. We need to have network visibility on everything. We need to monitor every byte that goes in and out of our system. And I was just like, you're not the one maintaining this. This is very terrible, and we don't have enough money to ever implement this. It's worth to actually take a step back to actually analyze the kind of things that go wrong. Monitoring for unknown unknowns, perfectly fine. Known unknowns, goodness, I keep getting confused about that one. Monitoring for known unknowns, perfectly fine. You can add as much monitoring to it as possible. It's just that if you don't understand the context, why things are happening in your system, why like the whole flow of data through a system, through sampling the data that you get, you're never going to really find the answer to any of these questions. You're basically going to have an uninformed view of why something is broke. Like, oh, the database has gone down. Well, we'll just add more databases. That will fix the problem. Or you'll do something like, oh, the service is down. Well, we'll just add more services to the problem. That's not a solution. That's just bandaging. And so, next one. Engineers need production access to be effective in an observable system. And I don't mean they need SSH access to the services running their servers. That's silly, and if you're doing that in 2020, you should probably rethink your strategies. What I actually mean is that they need to be able to own the data which is produced by their service. They need to own the outputs of that service. They need to be able to actually own the deployment pipeline that gets their service from conception or code changes to deployed or reverted or so on and so forth. They need to be able to be on call for that service. They need to have complete control over that service because in the end, they are the ones maintaining it and they should be the ones to actually keep this development going forward. Having your SREs own like half of the thing and then having your engineers own the other half doesn't quite make any sense. And it also doesn't scale. Oops, we need to press that. It also doesn't scale. There's only so many SREs that you can hire into a company, whereas you can hire as many engineers as you want into business teams and stuff like that. They should be the ones to maintain it because they know what it is that's actually happening in their system. The other thing that we've learned from this is that no observability means that you're missing some opportunities. If you don't know how data is flowing in your system, you sometimes tend to miss things that your customers are actually doing with your service. And as we found out at TransferWise, people use our service in quite interesting ways. For example, why do we have a spike of customers using the site, but not a spike of money being transferred through our site? So I think it's a bit late, but TransferWise is a money transferring site, so we expect people to, when they come in, they submit a quote for what they want to transfer, and then they fund us, and then we move the money, and so on and so forth. So when we see a spike of customers using the site, and not a spike of money being transferred, we're just like, what? What? Are we being attacked? Is this DDoS? So, for example, we saw this exact thing on Brexit. And I'm sorry, as a British person, that I keep mentioning Brexit. I'm sorry on behalf of all British people. Anyway, what we saw on Brexit Day, on the parliamentary vote on Brexit, was that we saw a spike of users using our service. And we were just like, okay, that's cool, it's a bit weird, but why aren't we seeing other services doing the things that we normally expect them to do? Are we under attack? So more teams started digging into the problem and found that, like, we're seeing an increase in number of users, but are we not paying out? Are we not paying in? Is there like something broken with our service? A lot of engineering hours went into trying to find out whether or not we had a problem. We didn't. And a lot of hours went into sort of reacting to the problem that we were supposedly having. And it's foolish. It's spending engineering resources chasing cars, basically. We had the exact same thing during the UK general election, 2019. I'm sorry for keeping mentioning Brexit. What the difference between that time and this time is that we had much more observability in our system. So when we had a spike of customers not using our service but not transferring money, it was actually our customer support staff who noticed that, hey, this is something that's happening. Instead of us finding out preemptively, actually after the fact, we found it during the thing. So our customer support staff come in and say, hey, we see a spike of people making quotes on our website but not actually depositing money. Can we take a look to see if there's a problem? Okay, so a few teams get together with their observability thing and answer the question of why are more people using the site but not transferring money? And as it turns out, what we discovered is that because TransferWise has this interesting feature where if you make a quote, we guarantee that rate for a period of time, people were basically just making quotes for a substantial amount of money and sitting on it waiting for the election results. That's right. So we were basically able to just, instead of having people watching the parliamentary debates for God knows how many hours, basically just waiting, seeing what's going to happen and then reacting to it, we were basically able to go, okay, so instead of dedicating entire teams of engineers to try and react to this problem, we were able to be proactive. We were able to have the money available just in case something went wrong. Everything went wrong. At least on the UK election side, in my opinion. Anyway. Another thing that we learned over the longest period of time that we've been doing observability, which is about a year and a half, is that the more observability in your system means more opportunities for doing or having production excellence. What I mean by production excellence is more resilience to failures, more opportunities to tackle engineering debt. So, as your service becomes more observable, engineers are basically able to make more informed decisions about what it is they need to work on and whether or not it's actually worth spending a lot of time doing this particular thing. It is the common refrain of every engineer when they see tech debt to fix it immediately, whereas your product engineer will absolutely, your product manager will absolutely tell you, don't work on that, work on product features. And if engineers have more data about the kinds of stuff that goes on through their system to see which code paths are actually the hottest, they would be able to go to their product managers and go, hey, we have tech debt around this particular area of our code. And as you can see, it would be worth spending a week, a month of engineering effort trying to fix this problem because it would make the site faster, make our service more reliable, or we need to extract this out because it's causing reliability issues in our service. And so what we've seen in TransferWise over 2019 is this. So this is a graph of the number of incidents we've had and the amount of time in hours it's taken to resolve them. At the start of the year, we're roughly going from about 40 hours or something between the instance starting and the incident resolving. As the year progresses and people get better at observability and having more opportunity to fix the things which actually matter in their service, we see the mean time start to go down. So as of the start of this year, instead of it being 40 hours to resolve a particular problem in the service, it's now only 15 to 20 hours, which is much, much better. Transitioning from monitoring to observability is hard, and the reason why it's hard isn't a technical problem, it's a people problem. People are squishy and they have feelings, especially engineers who have a lot of feelings about a lot of things. And so you need to be aware that they have certain ways of doing things and they've built processes around doing that. So when you come in and say, what you're doing is wrong, you should do this, you had better have a good reason for doing so. So the way that I sort of approach trying to do observability at TransferWise, at least to try and make people more aware of the problems and to actually do this, is to talk to them. I talk to engineers quite frequently, and I know quite a lot of their problems. And as I talk to engineers and find out and discover like what problems they're having with their services are completely unrelated to anything, or like what ailments or who they hate this particular week, you get to have an idea about which particular person's particular problems are more suited to more targeted sort of action. And what I mean by that is to find a champion. Find many champions as you can, because in the end, it's going to be engineers who are going to make the system observable. So you want to find someone who is susceptible to encouragement if you talk with them enough. Make them aware of the problems that they're having in their service. Make them care about observability, because most of the time, most engineers have never heard of this term before and don't know what it is and don't actually care. So make them care about it. Work with them, pair with them, walk them through what the best practices are. And when you have that one service as an example of what observability is, point to them and go, hey everybody, this is what observability should look like here. This is what you'll get if you do this. It'll prove much better than just trying to do a top-down approach where you basically try and force product managers to implement observability. And this also means that you're changing the culture about how engineers actually see monitoring and observability. So the point is that when you eventually leave the company, the culture of needing to be observable and needing to have like all of the workflows and stuff around observability doesn't leave with you. There is like a common theme of when you're not looking at something, or if there isn't the champion to continue doing the observability practices, or the one guy who implemented observability in the system, no one else cares about it, once they leave that team or transition from it, that's it. Observability is dead in that team, and it's very unfortunate. So you'll want to try and sort of change the culture by finding engineers who are more susceptible to actually the ideas of observability. And there's other ways you can do that rather than talking to engineers, which is to take the aggregated approach, which is to make loud noises. So what I've done personally at TransferWise is to write a blog post about it and present about it in the tech channels that we have. And what I found is that once I presented like what observability is and the challenges that we have at TransferWise are, there's a few engineers who come up to me and go in a sort of interesting way, they go, James, this is the exact problem that we've been having, and I've never been able to put it into words. How can I fix this? Can you please help me? And I go, yes, this is exactly what I wanted. Yes, all according to plan. And the last thing that you should probably do, and it's really, really, really good, is just to listen to what other people are actually doing in the observability space. I had no idea what anyone was doing in observability when I first joined the observability team. And it's only through listening to talks, finding out and talking to other people, finding out what the current lingo is, what the current problems are, I was able to sort of make a TransferWise oriented observability approach that would move us from having sort of like traditional unobserved data towards having more observable systems. And this process is going to take time. I've been doing this for about 1.5 years now, and it's only recently that I've sort of looked into our business team's plans, and almost every single one of them now is going, we have an observability problem, maybe we should fix that this quarter. I'm just like, yes, this is exactly what I wanted. And so I'm going to be very, very happy to add the Spotify talk next, because we're going to have that exact problem soon. Anyway, thank you very much for listening to my rambling, and yeah.
Give it up for James. Thank you, James. We've got 3 questions from James from the audience. Now, a 4th is coming. So, the first one is, do you think domain-agnostic observability is possible?
Domain or data?
Domain-agnostic, it says.
Domain-agnostic observability. That's a good question, one that I don't have the experience to answer, mainly because I haven't had any experience of it right now, but I'm assuming that once your observability practices and your tooling is sufficiently advanced enough, yes. The reason why I say yes is because I've had friends at Facebook basically say, like, we have one golden tool which can do all of the things in observability, and I tend to believe them, even though you shouldn't.
Okay. So the next question is, who are the people, Twitter handles, to follow on observability front?
So I'll just give you the one, because she's a massive shit stirrer, and she will basically dive into everyone. So if you follow Charity Majors or Nipsey Tipsy on Twitter, you'll basically get a handle for almost everyone in the observability scene. She's quote retweeted almost every single one of them at this point. So if you go through that, she's basically the gateway to observability. She also has quite a lot of blog posts and stuff around the culture of observability, the transitioning from traditional monitoring, stuff like that. And from her, you can find out other people like, what's his name? I only know him as Monk, who does a series of posts around observability in his kind of company, and production excellence and other things, and so on and so forth. So yeah, it's easier just to go to Nipsey Tipsy, and
obviously you need to follow James as well.
And also follow me, because I just retweet her every now and then, and retweet other people, and I also post about, I don't know, food I've eaten.
One question says, what tools do you use to have observable systems?
Okay, so we're still in the process of sort of aggregating all of our tooling into like the one golden tool. But for now we have, we've got Grafana for dashboarding and Kibana as well for some teams. We have an ELK and an ELF stack, an EFK stack. So that's Elastic, Fluent, and Kibana. We also have a Logstash one as well, because we're transitioning away from the Fluent side of things, because it's absolute garbage. We have Prometheus for metrics and stuff like that, and we use Vanos on top of it to aggregate the number of Prometheus instances that we have. We also do a lot of just random stuff with random bits and pieces. So we're using Facebook's Prophet library to try and experiment with anomaly detection using metrics. I'm sorry. I'm definitely going to use your tool when I get back to work. What else? I think that covers like the main ones that we tend to use on a day-to-day basis. But as I said, we're trying to cut that down. Having engineers go to 5 different places to get data is basically 5 different sets of data, and that's terrible, especially from an engineering experience.
Alright, let's go with the last one. Are you observing the integrated service providers connectivity and how?
What does that even mean?
Anyone who wrote the question wants to explain what he meant by that?
Is it...
Hey. Give me a second. Expand.
Thank you. My question in general is that you are connected to a variety of external systems.
Ah,
Like
right.
through the integrations, and obviously these are one source of your challenges.
Yes, they are, and it's very unfortunate. So there's only so much that we can do with the observability of external partners and stuff like that, but we do try to do our best. We do try to work with them to actually figure out whether or not they are up or not, but since we are dealing with banks, they are sometimes unreceptive to that kind of suggestion. So a lot of the solutions we have tend to be on our side. So we'll do things like making sure that the files that they're meant to send us are actually available for us and stuff like that. But we do have a very limited amount of option with our partners, especially when they're unwilling to sort of help us.
Alright guys, you can catch up with James during the break. We're going to have a break now for 15 minutes and then we'll continue with Anastasia and Alex. So, see you around in 15 minutes and we'll be around. Everyone is around. Let's move on. So the next speaker is coming from Sweden and she's working at Spotify and she will be talking about observability issues at Spotify. So, please welcome Anastasia.
Hello everyone, it's a lot of light, I'm just trying to move outside so I can stand. I might very well disappoint the previous speaker because I'm going to speak about data observability and not the service observability, even it was the first thing which came to my mind when I was asked to speak there. It's just like observability and of course the service comes into mind the first thing. So that's the agenda for the next 30 minutes. I'll try to go quick through it. So once again, who am I? I'm Anastasia and I'm the engineer at Spotify. I work with data and backend systems and I work mainly with GDPR and encryption and building infrastructure to that, but I'll talk more about that. Wait, I think this was the wrong side. So what do? Right, I'm part of the data infrastructure team. And my team owns one of the biggest Spotify services. We have around 1 million requests per second, and it's the service which gives out the encryption key. So whenever user logins or tries to access the playlist, it needs to encrypt the URL or encryptions of some personal data. So we have a very big service, but we also own one of the biggest pipelines for data pseudonymization. So whenever data comes in, nobody can access the raw data besides some service accounts, and we encrypt it or pseudonymize based on some set of rules. And yeah, so I could have spoken about this service, but I decided against it. One of the reasons is whenever we were trying to build it, we took Google's SRE book and we implemented everything according to it, and we were happy with that. It basically works. Compared to the previous speaker, which I'm referring to you all the time, sorry, we own the service and we're on call for that ourselves. So it's the whole Spotify concept that we don't have a SRE team at all and we own the shit we built. So if we don't have enough observability, well, it's our own problem. Another thing why I chose to speak about data. Well, the specific of our service is very read heavy. We read a lot and we don't write that much. So what happens, the worst thing which happens, we are down, we are missing a lot of read requests per second. Fine, the moment we are up and operational again, we are processing them back. It doesn't quite work the same way with data. Yeah, so here is where the data coming from. So we have a lot of platforms like mobile, web, whatever. We have event delivery system, we have pseudonymization pipeline, and we store the data somewhere in the cloud. So we have around 8 million events per second we need to process in a batch manner. We are trying to build the streaming prototype, but it's still a prototype, we'll see. because the data loss is the concern, and it's very rare that you don't lose the data during streaming. So, just a bit of scale, it's 8 million events per second. The largest event hourly partition is about 8 billion events. And we have 500 terabytes of data per day we process. We have more than 100 unique event types published and defined. We used to own the largest Hadoop cluster in Europe, and we are very happy that we don't own it anymore. Wrong side again. So how does it feel to be on call? So that's, as I said before, to be on call for the service, well, you misread the requests, fine, you're up and running again, and then you're getting them again. With data, it's not quite like that. Every time your infrastructure is down, your data just keeps piling up, and your downstreams to recover, the time just grows exponentially. And it's, during the incident, you always need to make a trade-off, like how to recover and run it at the same time. You start running weird issues with quotas, with disk size, disk space, amount of workers, and whatnot, and you're trying to call Google in the middle of the night and say, like, can we have more of? Like this data, like it's very big numbers, and who needs it? It's A/B tests, one thing. Another thing, developers put a lot of information to debug the product, and most important data is our business critical data, is amount of signups, because we're a public company now and we want to report it. And of course the royalties reporting, because every time you listen to a song, we are paying to the artist. And they want to make sure that we really pay every time someone listens. Okay, that's not the latest version of my slides, but actually this has low connection to observability at all, but I just thought, I have been speaking to a lot of companies who runs big data, do some analysis, and we realized that, well, not everyone is using data annotations. So a lot of people parsing the data and basically we don't know what it is. So it has low relation to observability as it is, but in order to your data to be discoverable, in order to know what to join on, etc., just annotate your data, make it once, take the pain, and live with that. That was an example, nobody could read it, so I'll skip it. So monitor your pipelines. We have our own orchestration system for running the pipelines at that scale, and it reports the state, so it collects all the data automatically. It's no metrics you define or can skip. You know the execution and running time of your pipeline. You can alert every time, for example, your pipeline runtime increases like 10%, 1%, whatever, and it can actually point you to a lot of problems, not only with the size of your data and not only the skewness of your data, but also like, well, are you doing something stupid? You're not optimizing your joins good enough, or something had changed. Another thing we do, like since I work with data pseudonymization, the worst thing which can happen to us is we produce corrupt data. It works like this. It's you join two data sets, the data sets you have, and basically the keys, the encryption keys, right? Every time you can't find the key to join on, you encrypt your data with random key, which means the rubbish data, nobody can use it. Count your data. So basically we have counters on a lot of things, and we have a special service which implements the alerting on that. So every time you all of a sudden start giving random key for more than like 10%, well, throw an alert and look at that. Money. So data processing is super expensive, especially at this scale. So I pulled this data and I was wondering where is this cost comes from. 1/3 of the cost is data flow, it's basically processing of it. Another third is storage and query, BigQuery. And this is the real incident. I removed the dates, but basically here are the jobs, and on the y-axis is money, and on the x-axis is time. So basically we filter jobs which cost more than $100 per job run. And all of a sudden we saw that after a certain date, the amount of jobs when shaking, the amount of jobs drastically increased. So a lot of more lines on the right side after the incident happened, and basically it's nothing to do with us and no our code changes, but it's the changes on the cloud side. So Google started to do something different and we got that behavior. So it's always nice to have alerting on the cost of the pipelines. Another example of cost monitoring, like everyone knows download your data button, right? Everyone has it, like Google has it, Facebook has it, Twitter has it. So we actually monitor how much does it cost every time someone presses the download button, how much we do a paper request, how much every pipeline which contributes to the end result costs, and basically very interesting to know how many people do actually open it, because you get a link, and it's only 25% of people ever open whatever we send to them. Right, since storage is 1/3% of the, like 1/3 of the cost, would be nice to know how the data is used, right? Because you can use the cold storage, for example. It's basically the storage is cheap, but the access is expensive. Would be nice to know from which region is it accessed, because then you can really decrease your I/O costs significantly by just knowing that and optimizing for that. And then retention. Well, people love their data and they're so scared to remove it, they will never do. So just to set up a default retention of, like, doesn't matter how many days, will save you cost. SLAs for partition. So we came up with this thing that we divide all our data into high priority, low priority, and medium priority buckets, and they have different SLAs for alerting on that. Basically it helps, like, first you don't wake up for every partition which is late during the night while being on call, and then you know the priority order how to recover if something is alerting. Also, we monitor our pipelines on failures. Here is just example, but I realize that it's very small. But basically, you can alert if your pipelines, like say, let's say, fails 2 times in a row. You don't need to wait 6 hours until partition is late. Or you can say, like, okay, if my pipeline runs for more than 2 hours, you can alert on that too, because what we saw very often that sometimes they got stuck one way or another, and like Google does not give the resources back, for example. So it's like if it runs for more than 2 hours, then just let's alert, kill it manually, or do something with it. Dashboards, we love dashboards for pipeline too, it's not only services. So basically we also made a system which makes a dashboarding super simple, and it comes when you define your pipeline, so the dashboards appear and they come. And it's nice if you combine your upstreams and downstreams. So without going into logs from the dashboard, you can see, oh, it's failing because my upstream is failing. Right, we love this word BCD, business critical data. Whenever we are late with that, the whole company is screaming. So it gets high SLO, special treatment when recovering the data, and very special observability when it comes to the data loss. So one of the cornerstones, how to prove that your infrastructure is not losing any data. Right, so that's how the event delivery system works. You have some, we wrote some SDKs, like for iOS, for backend, for Android. There are some services and they're trying to meet their data to receiver service, which tries to put it to PubSub or any other messaging queue. And then we do the application and make our repartition, pseudonymize and make our repartitions available for everyone. So the idea is, how can we prove, since we're a public company, that we are not losing any data there? It's kind of, it's not trivial to solve, because like who is watching the watcher? Because we implemented the counting service. Every time the SDK attempts to send something to the receiver service, we just count an attempt, and we know for which event it is. Also, receiver service, it can reject the message only when it cannot parse it. So instead of just blindly rejecting it, we are wrapping it up in a proper event, and we are putting it in another PubSub rejected topic. And there is a streaming pipeline which watches it and alerts whenever something starts appearing there. And we have also a batch job which is called compare, which compares the counters after all kind of did application and everything versus what reported the counting service, and it gets we get an alert if it's something below 0.01%. That's the difference, and that's what we tolerate. But it is alerting, and it's kind of who is watching the watcher, because if this one is down, can we trust another one? Shall we re-implement the whole logic, and who knows where do we do it right or wrong? Or what if Google is down, like our Kubernetes is completely screwed, so what do we do then? I mean, then probably Spotify has a bigger problem to solve than the counters. So the bottom line is like, it's kind of tricky to be part of infrastructure team because, well, you're not generating the direct value, like, right? Customer can see it, you're not a feature team, nobody will pay for your effort directly. So keeping your cost in mind is really, really good thing. That was it. If you have any questions, I think that was it about what I wanted to say.
Right, we got some questions for you. The first one comes from Hadoop fan. He says, what values were you expecting from Hadoop and why did it fail? And what do you use instead?
Yes, so Hadoop. Actually, we have an urn in the office where it says Hadoop on it. We ordered it and we made a pure proper funeral procedure for our Hadoop cluster. So the main idea is like data proc and everything to do with the physical maintenance of the thing. It does not really scale with Hadoop, and it was more expensive at the end than to let someone to run it in the cloud compared to what it was before. There were other things because we started to remove it like a couple of years ago. I was not exactly in the team, but main pain was the scalability. It didn't scale out automatically. If you want to solve some problem, it's always like the trade-off of the money and effort. If you need to quickly solve something and just throw in some money, now it works with Hadoop. And to spin up additional nodes was always the pain. So that was
it. What do you use instead of Hadoop now?
We use data flow jobs in Google.
All right. What business KPI numbers are important for your service or in general for Spotify?
Business KPI?
Yes, business KPI numbers.
Well, if you are part of the deep backend, there is no direct business impact. So it's nothing to do with user signups or listening, but the business KPIs for Spotify in general, I think it's the number of users, paid, not paid. The advertisements, because we are paid, like it's advertisements is one of the business for the free users, and amount of songs listened per user because we are paying the royalties. None of it is reported by with the service which hands out the encryption. Good or bad, I don't know, but that's how it is. So no like business critical things.
Right. This is a long one. Do you make any business or architectural decision based on the data collected on GDPR costs? Or what do you collect it for?
Yeah, so we definitely yes. So the for example, GDPR, there are many aspects to the GDPRs, right? For example, the right to be forgotten is the interesting one. So if I want to opt out from the service, that means what? That means someone needs to go and delete all my data everywhere. Like the architectural decision taken here was that instead of having like a batch job or a service, or like since it's microservices nowadays, it's kind of tricky to go and delete from every database. So what we did instead, if you are to be opt out, we just go and in one place we override your encryption keys, so basically null them. It's null strings in the database. Your data is still around, nobody can use it. Right, so that was the architectural decision made by us because it's kind of cheaper to do it that way. Another example of GDPR2 is, for example, when you press download your data, what probably there is some data which you are not interested in. Like, of course, you get all the main data, like your search history, your listening history, your all account details and everything, but kind of how much data and for how long back are you expecting to receive it, forever and ever, since you joined the service for 7 years? Will you really look into the 7 years of your listening history? So the decisions like that, you kind of, to collect this data costs, right? And there is like some kind of reasonable amount saying, okay, 25% of users even look into that. So what about if we give them like X amount of years or months back, and then basically that's it, and then we'll see if they come back and ask for more. There is, because the GDPR is very vague, and then there is a whole procedure people can follow if they want to.
All right, I think Ricardo was so fascinated by it, also he wants to ask the question.
Thanks. It was a nice talk. Actually, we started discussing before. So, on the watcher problem, so to me, it really looks like a distributed transaction problem, because we want to ensure that whatever it doesn't matter, you just do, well, it really looks like a distributed transaction problem. You have a bunch of systems communicating through message systems, and you want to ensure that everything you write either is there or not completely. Like when it's not there, you know it. So, yeah, the question is, did you try to implement any sort of saga pattern to face comment approach that ensures that everything you write is there, or you just what you're trying to do looks to me something like exactly one semantics in some stream processing solution. So did you try any distributed transaction approach or saga pattern across microservices, or any exactly one semantics?
Yes and no. We've tried some of it, but the reason is, like, at that rate, we don't need to know that everything we write. Because there is a lot of data we don't care about. You browsed on the app, we missed it, like, yeah, okay, bad luck, what can we do? Or you lost your, search history, bad user experience, that's about it. But there is more logic to that than just like lost or not lost, and in what circumstances. And it makes more complicated the things when, for example, the devices you can download and be offline, and then you go and report later on. So what do we do about that? The skewness of the data comes into the account. So with all of that, we decided to be as simple as possible. So that's one thing. Another idea, like the most things we're worried about is actually the duplication. And one of the source of duplicates is, for example, Google pops up, because they ensure that they deliver message at least once, right? But they deliver more than once in most cases. That's one thing. Another thing is retrials on the mobile devices. Sometimes they send more than once. So the duplication is the biggest part. And the idea there is like to make some kind of models and train it on it and test it on it extensively and make sure that, because that's theoretically the only place where we can throw it away intentionally. That answers your question.
Of course. All right, thank you, Anastasia. Give a big thank you for her. And I'm happy to announce that I managed to fix this app running stuff. And now we're going to go to the last speaker today. This is one of my partners at Timetrix, and he's going to be talking about data agnostic observability, an example of growing packs. So give a big welcome to Alex from Timetrix.
Hi guys, I'm starting with some unusual topic, okay, because we talk about some data collecting from software systems, from different kind of measurements, but I have some sort of hobby, and especially if you live in the city, especially if you live in a northern country, which have long winters and less light, you need to create some sort of microclimate. And we talk about our engines that we developed based on Java stack reactive 1, and it was quite curious for me how we can adopt our engine to process data collected from sensors. So here in that case, I didn't set up production quality sensors because for me it was more important to set up a so-called pipeline where I can so-called test whether this approach works, and you can see what I have or not. No? Oh, okay. So yeah, if we talk about urban gardening, it's quite easy if you live somewhere in the Mediterranean climate. You have some house and so on, but in the city conditions, you have limited abilities to build something. But if you talk about plants and flowers, it usually give some sort of happy feeling because we love if we have some sort of animals, cats around us, and maybe some sort of flowers. And it's quite tricky to grow some specific species, some specific strains. It's very easy to put some random flower, I don't know, in your house, but if you want to work with some special, which needs some specific requirements, then you need to be some sort of clever. For example, you need to hold a microclimate, and I have a different species. And for example, a leaf tree, which have a lot of fun in the summer, you can see, but have a problem in the winter, too dark, and usually it switch on life cycle to so-called autumn, try to drop off leaves. And actually there is some tricky moments because every plant species has own requirements or preferred range of temperature, relative humidity, light, air conditions, and especially there is even differences between different plant stage. So in seedling or early stage vegetation, you need a high relative humidity, for example, a lot of ambient light. But if you have a bloom phase, you need less humidity, you need probably lower temperature, just to make your plant believe that this is autumn. And this is my papers, different strains. This guy is quite hot, but this is hot too. Actually, it's quite tricky to grow them because they are very sensitive to a change of temperature. They usually grow with some sort of tropical climate in Mexico, and even if you grow some sort of paprika, which can tolerate a lot, then these guys are not. And this is start, so you have seedlings, different sorts, apocalypse chocolate, super hot beast, but you need to measure to be sure, because again, you can have some sort of on-demand sensor, so you need to check it with your own eyes, but if you need to have a clear picture of what's going on, you need some sort of pipeline which can save measurements somewhere. So the example was quite simple. I had another temperature sensor, digital temperature and digital relative humidity sensor. I have an ambient light which checks the amount of light, and quality of air, specifically particles, amount of particles in some volume of air. And data sent is to our Arduino controller, very easy, some kind of Lego, and then all data was sent to InfluxDB, which is deployed in DigitalOcean, costs almost nothing, And how it started, so you can see there is some sort of creating hardware with my friend of mine, and guy who helped me a lot. And this is a test setup with sensors on my plate, connected to Arduino. And okay, so this is a data collected from our sensors. It's more than 1.5 millions of measurements, which collected every minute. And you can see we have a different kind of things like light, so you can see those spikes, because again, when you switch your peppers to bloom phase, you need to make a trick that plan did this autumn. You make a shorter of light day, and we have a high humidity. For example, I have a high humidity problem, because if you have some plants, you have a normal watering, and if you have a quite, for example, let's say in a closed room, you have some amount of plants, then you have a problem with vaporizing of this water. And you can see that I have some sort of spikes in the beginning, and I fight with this problem by dehumidifying. But again, without ability to understand what's going on, I missed it. And quite interesting thing, because this is a data which is written from the quality of air sensor. And you can see that starting from the beginning of November, we have a reducing of air quality in Tallinn. So, do you have any ideas why particularly this can be?
Everybody's eating with wood.
What?
Everybody's eating with wood here.
Some sort of, yes, it's actually it's related to climate. So if you have a colder weather, we have a station which starts to work to heat water for our apartments, and as an output we have burning particles which is flow to the air. And you can see we have a quite warm winter right now, and actually we have a quite mild autumn as well. So this graph is related how intensive worked one of the stations in our near the sensor was deployed here. And actually there is another problem which I didn't understand. Last week, ST Express published a cool article. What is the secret behind the poor air quality in Tallinn? Especially if you have a car, you washed it, and after 2-3 days you have almost quite a dirty car, and you can remember that every spring we have a city full of dust. So we have some washing machines, but it's usually pictured that we have some sort of dust. And actually, it was quite cool, because you can see in articles one of the main source of that air. So there is a production site where some sort of raw materials for construction works, and you can see a point where sensors were deployed. So you can see it also can catch if something is going on with this site construction. So actually, yeah, I had a box with microclimate collected data from the sensors, where I can set up the first condition, and if something goes wrong, I can have a quite fast reaction on top of that. And I guess there is a problem with playing the videos. Yes. Or no. So yeah, there is a problem playing video, but this is start of the video, this is not the real speed. No. Okay, it's a bad slide presentation platform because we didn't play any videos. But the speed of processing, so we had, again, as I said, we had almost 2 million points of measurements collected in 2 months. The speed of processing, when you do it on demand, is approximately, on a quite small machine, approximately 10,000 events per second. If we make some sort of pure deploy, then we will have in order of magnitude larger. The main idea that you can see some sort, yeah. Main idea is that usually, if we talk about data storage, we have 2 classes of tasks. We have online transaction processing, where you have a lot of updates, where you have a lot of short inserts, so you need to process a specific row of data very quickly. Or you can have some sort of analytical processing, where you need to process a huge amount of data with those grouped by, and so on and so on. So it's different tasks, different requirements. Actually, in our region, we take an approach, everything is a stream. So even if you set up an analysis on demand, it's scheduled to the stream as well. And it gives you ability to not to split different classes of work, but process everything as one, as a stream. And it gives you ability that if something is worked on demand, then the same functionality will work near real time at the speed with thousands and thousands of events per second. And comparing, for example, there is a commercial product, Anecdote, which built on top of Hadoop, and Hadoop is dead because even Google finished last MapReduce jobs at year 2014. So Hadoop was born after Google published its white paper about MapReduce. And usually Google publishes something when Google understands that there is a problem with that, let's push it to everybody. And while everybody tried to implement some sort of Hadoop storages, they have some sort of infrastructure, Google at that time finished using that. And the main problem with Hadoop is that, okay, it's a quite large beast, it's hard to maintain, hard to set up, but the main problem is that comparing same amount of job, Hadoop will do it 100 times slower. So that's why, for example, on a commercial product, Anecdote, which are oriented on some anomaly processing built on top of Hadoop, needs minimum requirements 32 CPU and 64 GB of RAM. If you need more than 200,000 metrics, you need another class of machine because of Hadoop. And comparing with stream-oriented approach versus Hadoop batch, this kind of thing can process very efficiently on small resources. And actually, we have plans because we test pipeline with the urban garden at home. We want this spring to put some production-grade sensors into vineyard of our friends, very metal. So those cedar, which you taste, is made by those guys. And we want to put this year production-grade sensors under the vineyard. So just to collect data, send it to the cloud, and that's all. And we can, for example, tell that something is going wrong or where you need to fix something quite fast. And again, if we talk some classical industries like agriculture or some sort of manufacturing, then usually guys do not want to know anything about servers, about infrastructure, about how to deploy or make backup of this data. Everything that they want is just put some, box which writes something, and they want to open their phone and check that their situation. And it will also like interesting case, which we start this spring. And as a result, we try to open source our engine this April. Main problem is you can't go open source without documentation, without all the instruction how you can easily set up something, and we are linked on that you need something like 1 or 2 commands. You can run, you can just run some exported data in CSV, and you can set up something very quickly. So I guess, yeah, documentation related to API, and we want to open our code in April. This is Java stack, reactive one, Java 11, and even this is a set of services, event-driven system, and even on a service level, we also have functional approaches. So everything is functional, everything is stream, even on service level, everything is stream on architectural one level, and taking this as the premises, we can set up performance so fast that when compared with some classical stacks as Hadoop or some another approach, there is a huge, huge difference in terms of costs, in terms of performance, in terms of maintaining it, because Hadoop is a quite hard beast, which is dead.
All right, having said that, thank you very much, Alex Mitchell. We're almost done. One question. Anyone wants to ask a question? If not, then I'm going to proceed with very important organizational information. So, we are not done here. We will proceed to the back room, and please use the room to this side on this wall. So there is this area is all to us. We can use it after the hangout. The only thing is that we will kindly ask you to pick up your clothes from the wardrobe, because the ladies that you occasionally meet and start talking Russian with you, if you do that, please just run. They are just a bit, picky and that stuff. So it would be very cool if you could pick up your clothes from the wardrobe, so we don't have to deal with that. Please abstain drinking alcohol in the entrance area. That's apparently also a problem. But apart from that, you'll be playing with a robot in this area here, and Mash Machine will be entertaining us further here. So let's hang out, let's chat, and thank you very much for being tonight here. We hope to see you next time. It's definitely not our last event. And if you have any requests, any wishes, and you want to contribute, please just give us a buzz.
Yeah, in contribution, actually, we have quite a cool stack. And actually, main problem for a junior developer, okay, I'm working with 3 years in some enterprise, and I want to find a new job. Can you show your code? No, it's in the A, so I can maybe test the case. But again, working with some open source engine gives you the ability to show your code or show what you can out of the box. So
join the Time Tricks movement. All right, let's have a drink. Thank you very much.